The error kernel pattern allows us to keep important actors relatively safe, but there are cases where we need to not lose state at all. We need to persist it. In this lecture, we look at how actors can do that. The first observation is that losing state due to a restart is not the only thing which can happen. Not only our software can be buggy, our hardware can make mistakes too. For example, the computer's power supply might fail, or there might be a power outage in the whole region and the data center goes down. In that case, the running state of actors will be lost because it is only kept in memory. If we need to keep that state across, for example, the power outage, then we need to make sure that it is stored on a hard drive, for example. When the power comes back on, we can then read the last persisted state and start from there. The same principle applies when it comes to a softer source of the restart. The reason why we did it might be different, but what needs to be done is exactly the same. We need to store the result of successful processing, and once a failure has happened, and we recover from it, we need to recreate the current running state so that we can keep running from where we left off. There are two main ways in which state can be persisted. The first is to have the actor mirror a persistent storage location and do in-place updates of both. So when the actor's state changes, the persistent location is also updated. This persistent location could be files in a file system, or it could also be a record in a relational database. The other way is to not persist the state itself and update it, but to persist the changes which are applied to state. And this is done in an append-only fashion, meaning that these change records will never be deleted, they will only be added to. The current state can then be derived by reapplying all changes from the beginning. There are obvious benefits to persisting the state and doing in-place updates. The first is that recovery of the latest state can be done in constant time because you just need to go to that one memory location and read it back. The other advantage is that the data volume needed for storage depends only on the number of records and not on their rate of change. It is easy to see that if you persist the changes, you will always persist at least as much, and most of the time much more data than if you would just persist the records themselves. But there are also benefits to persisting the changes. For example, if you do that, you can go back to any point in time and replay history, audit what happened in which order, or restore a certain state, say from last Thursday, because you need to either rerun what has happened or you need to discard all the changes which have been done since then. During a replay, the code which handles the processing could also have, for example, been fixed because it had a bug previously, and that means that errors which crept into the current state can be corrected retroactively. This is not possible if you only store the current state because it will have the bug in it. You all have seen the third advantage at work. For example, if you were shopping at a large shopping site on the internet, which we all well know, if you look at the shopping cart and you put an item in, it is in the shopping cart, you might continue shopping, take it out, replace it by another one, and finally, once you go to the checkout, the current contents of the shopping cart is what you actually buy. If you only persist that, then the whole history is lost. But it might be very interesting to keep statistics. For example, this refrigerator has been replaced in 50% of the cases by that other one, and people can then learn from other people's decisions. Of course, these insights can also be used inside the company itself to organize their logistics processes. Storing all these events takes a lot of space, but space is comparatively cheap nowadays. And therefore, if profit can be made from analyzing these data, then it's well worth it. The fourth advantage has to do with hardware and how that works. If you write in an append-only stream, you can write a much higher bandwidth to I/O, to network devices and also to hard disks. The reason is that in-place updates need to at least appear to occur in exactly the order in which they were given, which limits the possibilities for optimization. Finally, persisting immutable data has the advantage we have seen throughout the functional programming course. Anything which cannot possibly change can be freely shared and replicated. There is no need to synchronize access, and whether you store an event stream to 1, 2, or 3 locations does not make a difference. This point allows the benefits of both approaches to be combined. Consider an actor which wants to persist its state. It writes events describing all the changes into a event log. Since this log is immutable, another process could take these data and feed them into a database offline, from which the actor could then retrieve the latest persisted state in constant time. Doing that for all changes can be the right answer in certain situations. For example, if there are multiple readers for that state and not only this actor. But if you only want to persist the state of an actor and put an upper bound on the time a recovery may take, then you can also use snapshots. So we have again our actor producing the stream of changes. And then to the side, there are snapshots, which it tags. At this state, when I processed that event, that was my state. And it can do so periodically to keep the time short between these. And if a recovery is needed, then only the latest snapshot will be taken and all events which came after that. Snapshots again have the property that they are immutable, so they can be written append only in an efficient fashion, and they can be freely shared. With this background, we can look at how actors actually persist changes. You can picture an actor that is persistent as one that keeps taking notes of things that are happening, things that it is doing or things that it wants to do. In Akka, this is made available by the persist method. We'll see the larger context in a minute. It is important to first learn what it means to persist an event. First of all, we must create the event itself. Let's say we have a class myEvent that we construct with some arguments here. Passing this into the first argument list of the persist method means that this event is sent to the so-called journal. We have here our actor that wants to persist things. And in the system we have another actor that understands a certain set of messages related to persistence. Calling the persist method means sending a message to this journal that we want to persist a certain event. The journal can be implemented in many different ways. It could write this to the local hard disk, which would not be perfect in case that hard disk fails. So typically it will also write it to some other hard disk somewhere else, or it might be stored in a different fashion. It might be in databases that are held in many copies in memory across all the globe. It can be any system that can make sure that whatever we pass here, the event that we want to persist, is actually held such that it will not vanish and that it is always there. Once that has been done, once that has been confirmed that the event has been written to disk and replicated and so on, the journal will reply to the actor with a confirmation. This confirmation contains the event. So the event travels once from the actor to the journal, is being persisted, and then travels back to the actor. As soon as this journey is complete, the second part of the persist method, this function here, comes into play. We receive the event as it comes back from the journal, and now whatever we do in here, we can do in the knowledge that this event is stored safely somewhere. We can rely on the fact that we can replay this event later. We know that it has been persisted. This is why we describe events as facts about the past, things that are certain and committed. In order to look at a more complete example, we introduce an actor that does something useful. In this case, it manages a set of blog posts. This actor understands a command called new post, which contains the string, the text of the blog post, and some ID, a correlation ID, so that when the actor replies either with a positive blog posted or a negative blog not posted message, we can use this ID to find out which post it was that was accepted or rejected. In addition to this external protocol spoken by the actor, we also define a set of events that this actor creates and emits. The first one is taking note of a post that has been created. And this is the post created event, which holds the text of the blog post. And the second one, to make this actor a bit more interesting, records when the user who has submitted this blog post has reached their quota. Let's say we have a really stupid limit of you can only create one post. We'll see that on the next slide. The final piece here is that the actor itself will keep state. It accumulates the posts that were created and it keeps track of whether the quota has been reached. And this is held in a class called state here, which holds all the blog posts and the disabled flag once the quota has been reached. Remember that the purpose of events is to describe change. This means that the events themselves are meaningful in the domain that we model. So we have blog post created and quota reached. But the events themselves do not know how this influences the state of the actor. The state of the actor needs to know how events change it. This is why the state object has an updated method which takes an event and then it reacts accordingly to what the event type was. If it was a post created, we make a copy of the state appending this text of the new blog post to the posts that are already there. Once we see a quota reached event, we just switch on the disabled flag. With these preparations out of the way, we can take a look at the actor itself. The first thing to note is that instead of extending actor, we extend persistent actor. This trait defines the persist method that we have seen earlier, and it also runs this process of sending the to-be persisted events to the journal and receiving them back when they have been persisted. In order to do this, the persistent actor must speak with the journal, must have a conversation that we do not see in this actor. This is why the receive method has been implemented in the persistent actor already, and what has been written there delegates to two new methods. The receive command method is the correspondent of the receive in a normal actor in that it defines its normal behavior during runtime. There is another receive recover that we will talk about later. The crucial piece that defines the stateful behavior of this actor is kept in a single variable called state. It starts out with a state that has no blog posts in it and is not in the disabled state. When this actor receives a request to create a new post, this will contain a text and this correlation ID, and in this case the actor checks. If posting has been disabled in the state, then the reply is pretty clear. We send a blog not posted for this ID with a quota reached explanation in it. The other case is the more interesting one. We want to create a blog post and we must take note of it. So first we create a post created event with the text and we persist that. Once this event comes back from the journal, we update the state of this actor. I have written a utility method here which does it. And then we can confirm to the sender of the new post request that this blog has been posted. In order to change the behavior of this actor to one which is preventing further blog posts, we also persist a quota reached event. This demonstrates the usefulness of this update state method, which I find myself writing typically, because this will just be expanded into a function that takes an event and applies it. So we can use the name here just like that. Now, what happens if this actor crashes? If the machine crashes that it is running on? When we start it again, the actor will process everything that it has persisted before. And this is done in the receive recover method. So whatever was successfully persisted, either this post created or the quota reached, will afterwards be replayed in this receive recover method. And here we simply take the event and update the state of this actor with it. This means that the state of the actor will go through all the same steps that it has gone through previously. Update state here, and update state there. The only thing that we leave out in this process is the other actions that are taken in response to successful persistence of events. While recovering, the sender of that blog post that we receive from the journal might not be there anymore. This recovery might actually happen several years after the blog has been posted, so sending back to that sender is pointless. But we need to update the state so that we arrive at the same internal state after recovery as we had before the crash. There is one important detail that I have glossed over on the last slide, and it is best explained using some flow diagrams. So what have we implemented? We have the actor and time going downwards, and we have the journal as the interesting parties. When the actor receives a new post, we have done several things. The first of which was to check whether posting is currently enabled or not. I'll mark that with this red color here. And let us say the check was positive, then we persisted the new blog post. Now, it takes some time for the journal to disseminate this event, to replicate it to all the storage locations, and to get back with the acknowledgement. Let's say it happens here. At this point, the function was run that we gave to the persist method as the second argument. And this was updating the internal state as well as sending the reply to the original requester. So let's say this is updating the internal state, and then we send back blog posted. Now the interesting question is, what happens with a request that comes in between these? When using the persist method to make this round trip via the journal, the persistent actor trait switches this actor in a sort of deaf state, or in a state where it does not receive new messages. This means that the new post message that came in at this point in time will not be handled until the previous process has been completed. This is necessary because this check here depended on the state being the current state. But we only update the state down here. So if we perform this check again here, we will find that the quota reached has not yet been applied. We will persist another blog post even though that was not supposed to happen. This is why the processing of this message is deferred internally until this point. There is another method that can be used. So we'll draw the second case. We have again the actor and the journal and their timelines. We have a new post coming in. We perform the check, and then we use a method called persist async. This will also carry out the whole round trip for the event through the journal. So it will come back at some point here, but it will not stop the actor from processing other messages in the meantime. This means in order to keep the actor's processing consistent with our rules, we need to apply the changes here already, such that when the next post comes in, it will be rejected because the quota reached has been applied. Now, what is left to do when the persistence round trip has been completed and the events come back from the journal? In this case, the state has already been updated, so the only thing that is needed is the blog posted message to the original requester. The difference between these two schemes of doing things becomes more clear if we consider that the quota will only be reached after the 1000th blog post and not after the first one. This means that most of the time this check will be successful and we will want to accept a new blog post. In this case, accepting a blog post is always deferred until the previous one has been completed. This means that this round-trip time through the journal determines the maximum rate at which we can accept new commands. In the persist async case, on the other hand, we can go ahead and have several new post commands outstanding. The round trip will be made. That defines the latency between new post and blog posted, but other things can be happening at the same time. This means that the maximum throughput of this actor for processing new blog posts will be much higher than in the left-hand side case. The obvious question is, if it performs better, why do we not always just use this approach? Well, if you look at the history that these graphs express, you can see that this actor here will always only be in states that have been persisted. It only changes the state once recovery will lead to the same result. If this actor crashes in here, then it had reached a state here which was never persisted. This means this can only work if this new internal state change here, which is not yet fully committed, cannot have any externally visible effects. For example, we must not reply to this new post that comes in here before we have actually heard back from the journal at this point. There are many use cases which can benefit from this, but keep in mind that this is not a general solution. There is one more aspect that these graphs can illustrate. Let's say the whole system fails at this point. For example, there is a power outage in the computing center and everything goes down. It is clear that the blog posted messages will not have been sent, not in either case. But it is not clear whether the change, the event, has already been written to disk and will therefore be replayed or not. What this means is that the persistent location to which the journal writes the events becomes the one source of truth for this system. Either it has been persisted, then it will be replayed, or it has not been persisted, and then the post has never been posted. This is a fundamental aspect of distributed systems. You can have only one source of truth, because agreeing whether the post has been posted between this storage location and the client that wanted the post to be posted is a process that takes time. It is not an atomic action that can be either made or not. The practical consequence is that the client which sent the new post is either interested in having the post made, and then it will wait for the blog posted, and if it doesn't come, it will resend it. For that purpose, it had the ID. Or that client might not care anymore, and then it will not resend. And then the storage location in the journal just determines whether the blog post was made or not. In order to complete this, let us look at the code that corresponds to the second way of doing things, using persist async. In this case, we do the check first, then we create the events and update the state accordingly. And then we use persist async to send the created event to the journal, and when it comes back, we can reply to the original sender that the blog has been posted. And we also need to cycle the quota reached through the journal. But when it comes back, there is nothing else for us to do because the state change has already been applied. When discussing that in a distributed system, you cannot have a distributed source of truth, there will just be one. We'd already touched on the subject that if someone is interested in something else happening somewhere else, then that someone needs to make sure of that, needs to retry things. This leads us to wanting better messaging guarantees than the at most once semantics that Akka and other actor implementations provide out of the box. What we want is that the message is sent and then resent if something got lost until it was successfully delivered. This is called at least once delivery. In order to implement this, the sender and the receiver of the message need to collaborate. The sender needs to be able to resend the message until it gets the confirmation back. And the recipient, of course, needs to provide that confirmation. It needs to acknowledge the receipt of the message. Otherwise, the sender doesn't know when it can stop resending. Now, messages can be lost in any direction in this exchange. And if the receipt confirmations are lost, then the sender will faithfully continue sending messages. So at least once does not only mean that messages are sent possibly multiple times, they will also be received possibly multiple times. So this is what at least once entails. But how does this relate to actor persistence? Well, if you need to be able to retry something, you need to take note of that, because if the actor that wants to retry things crashes, the machine crashes and so on, then after it is restarted, it needs to remember that it was about to do something. And this is not only true for the messages that need to be resent and keeping track of that shall happen. It must also encompass the acknowledgements, because the actor must also remember when to stop resending. Here we look at a simplified version of our blog post management actor that manages the blog posts for one user. This one extends persistent actor as the previous one, but it also mixes in the at least once delivery trait. This trait provides the deliver method. Now, when a new post request comes in, we persist that we want this post to be created, and when that has been written to the journal and the event comes back, we tell the at least once delivery trait that we want to deliver a publish post command containing the text to a certain publisher. Publisher is giving to this user processor actor as an actor path and not an actor ref. The reason for this is that you may remember that an actor ref is coupled to the life cycle of one actor incarnation. If the whole system crashed and is restarted afterwards, then the actor refs in the old system will no longer be valid. If you wrote them to disk and read them back in and reconstruct the actor refs and try to send to them, the messages will go nowhere because the actors will all have been recreated from scratch. The part of the actor identity that stays valid across such an event is its name. And that is exactly what is captured in the actor path. The other notable detail about the deliver method is that the second argument it takes is not simply an event or command. It is a function that produces one by inserting something here. What it inserts is a long integer number that serves as a correlation ID that we will see how it's used in the following. Now, as I said, the actor needs to remember that it wants to publish this post, and it does that whenever it sees its post-created message. So we also need to run the same processing in the receive-recover method. Normally, we would update the state of the actor in both cases, which I left out of this example. It is just important to note that delivery must be reinitiated after a crash. But what about the confirmations? We said that sender and receiver need to collaborate. Let us say that the publisher speaks a protocol where you can send a publish post and it will reply with a post-published confirmation, which carries the same ID that was placed in here. What we do whenever we get such a acknowledgement is that we inform the at least once delivery trait that this delivery has been confirmed with this ID. And it is also important to do the very same thing during recovery. Picture this actor crashing after 3 years and handling thousands of blog posts. Then it will, for all of them, see a post created and a post published pair, which means it will start redelivery of something that was 2 years ago and then immediately stop redelivery. Of course, the at least once delivery trait is smart enough so that it does not actually start sending the outstanding events or commands. It waits until recovery is complete. So deliver and confirm means putting it in the list of things to be resent and taking it out again. And only what is still outstanding after recovery finishes will then be sent to the publisher. When we talk about what messaging solutions need to provide, which semantics they shall give us, at least once is not normally what we say. Normally what we want to have is that when we send a thing, then once the messaging system takes this thing and goes about sending it, we want the messaging solution to make sure for us that processing happens for this item exactly once. We can capture this in a little sketch to make the responsibilities clear. We have a sender and a recipient. Between them, we have a way to transmit messages, which has at most once semantics. At least once is the responsibility of the sender. The sender needs to remember and resend things. Exactly once is the responsibility of the recipient. The recipient needs to remember what it has done and then avoid redoing it again. In order to demonstrate this in code, let us look at the publisher that we sent our blog posts to. This will be a persistent actor because it needs to take note of what it has already published. The user processor used at least once semantics to make sure that the publish post messages arrive at this point. And now we need to implement the deduplication. For this purpose, an ID is included in the publish post. We are reusing here the ID that is generated by the at least once delivery trait because that starts at 0 and then is incremented contiguously. When the publisher and the user processor start up, they will both start their ID sequence numbering at 0. So we expect the first post to have an ID of 0 here. When the publish post comes in, we check the ID to see if it comes from the future, and this means that we need to ignore it. It is something that is newer than what we expect. There is a message missing. Otherwise, if the ID is smaller than the next expected ID, that means that we previously confirmed this ID, but the confirmation must have been lost. So we just need to confirm it again. Otherwise, the ID must equal the expected ID, and this is where the interesting action happens. First, we persist the event that we published this post. Only once this is committed to stable memory, we get back this event, we inform the sender of this confirmation, and we do the actions of actually publishing the post. Let's say we modify some website to do that. As a last step, we need to increment the expected ID so that we can receive the next publish post command. This sequence makes sure that we persist the post published exactly in sequence for the IDs 0, 1, 2, and so on. During recovery, the only thing that we need to do is to keep track of what we have already published, what we have already confirmed. This process makes sure that we will persist the post published for each ID exactly once. Now, what happens if the machine that this actor is running on crashes at some point? There are several different points where this could happen. It's rather uninteresting if it happens here, because we would ignore things anyway. The most interesting part is within these braces here. Let us consider that the post published was persisted successfully. We start executing the function, but the machine crashes right here before we send the message. This means the same thing as if the acknowledgement that we would normally send back would have been lost on the way. The sender will retry the message. We will see, this expected ID is smaller as the one that we expect because persistence was successful, so we have during recovery incremented the expected ID. But what about the modifications to the website? These will not be retried. They are the responsibility of the publisher actor. We have persisted the confirmation here already, so during replay we do not modify the website again. That is the purpose of this block. This demonstrates that exactly once delivery of messages is not usually what you really want. What you really want is exactly once processing of the effects that these messages should have. This also should make it clear that no messaging solution can ever take care of this for you. If the machine crashes at the exact wrong time, then the message may have been delivered, but it has not yet had its effect. The underlying issue is a fundamental one. Performing an effect and persisting that it was performed can in almost all cases not be done atomically. You need to do either one, then the other, or the other way around. If you perform the effect before persisting it, then you achieve at least once semantics. Because you might perform it, the machine crashes, you have no memory that you have performed it, so you perform it again and then you persist. You have done it twice. The other choice is what I implemented on the previous slide, namely to perform the effect of updating the website after persisting that this has been done. And this achieves, as we have seen, at most once semantics. Commercially available messaging solutions usually pick the second of these alternatives, but if you have a choice, you should make it based on your underlying business model. What costs more, doing the effect one too many or one too few times? This choice to be made is usually between two evils. If you think about, you need to bill a credit card and you want to do it exactly once for one purchase, as is usual, then doing it 0 times is maybe just as bad as doing it 2 times. In one case, the company loses money. In the other case, the customer will be very unhappy. So is there not a third way? The key to solving this dilemma is called idempotency. An action is idempotent if executing it multiple times has the same effect as executing it once. It does not matter whether you repeat the action or not. We have seen an example of this on the previous slide, where the actor assigned the expected ID. No matter how many times the actor restarts and makes the very same assignment, the result is always the same. Combining idempotent actions with at least messaging semantics achieves effectively exactly once processing. We have seen that actors persist their state by recording the changes that they intend to make to it. Each event is a fact that represents knowledge about the past, and that can be freely replicated, shared, and sent around. Other components can use the events emitted by one to learn of that other component's progress and make changes to its own state. The state that existed at any given point in the past can be reconstructed by replaying the events that lead up to that state. Snapshots can be used to reduce the time that this takes, because if you use them, recovery does not need to start at the beginning of time, but it can be started at the most recent snapshot. Keep in mind, though, that snapshots do not represent the meaningful business events of the domain. They represent the internal state of a component. As such, they are less durable and less valuable than the events themselves.